All right. Welcome to the next installment of the Zoology of Exciton mini course. The species, I guess, that we're going to introduce today is one of the most important. It's called the charge transfer exciton. And what we're going to consider is the role of electronic coupling between different molecules in a solid, with special consideration of the operation of organic photovoltaics, which are important for future solar cells. So what you're seeing on this slide is a picture of a mixture of two different types of molecular species. It's actually a polymer and a small molecule. And the sort of messy spaghetti-like disordered blend is the key to the operation of this special type of solar cell that takes advantage of this special species of exciton called the charge transfer exciton. And so let's just recall the real space perspective on the different broad exciton types that we've seen so far. We start with the traditional Wannier exciton, which is an electron and hole bound together with an average separation that's quite a bit larger than the lattice spacing in the solid. So you have a small binding energy, large radius, that gives rise to that. And this is typical of your traditional inorganic band semiconductors. And so another extreme case that we talked about in the last lecture was the Frankel exciton, also called the molecular exciton, where you have an electron and hole bound together on a single, usually organic molecule. And so these would have a much larger binding energy because of their smaller radius. And you find these in molecular solids like the organic semiconductors that make organic photovoltaics. And so what we want to do in this lesson is think about the intermediate case where you still have a small size, but you're not on a single molecule. And this is the case of a charge transfer exciton, where we imagine a similar organic molecular solid as we had for the Frankel exciton, but now we allow the electron and hole to separate from one another and live on adjacent molecules. And so here you have a small separation, and so intuitively from the hydrogenic model, the binding can still be strong, should be less strong than in the pure molecular case. But it's not clear why this would happen or what materials you would expect to find this in, and that's kind of the topic of what we're talking about in this discussion. So why would a charge transfer exciton exist? In other words, what's the driving force for the electron and hole to separate by just a little bit? So there's a couple of different things you can say about this. The zeroth order thing you can say, which is almost a joke, is that in quantum mechanics, that which is not forbidden is mandated. And so in other words, if this process is possible, we have to at least consider that it might happen and maybe think about computing the extent to which it happens. So it's sort of a joke, but it's actually not a joke. To be a little bit more specific, there is always a small so-called transfer integral that couples adjacent molecules even in molecular solids. I mean, this gives rise to their conductivity, their band structure. And so the states are slightly delocalized, and so there's definitely some electronic coupling that would allow migration of charges. And then a third comment you can make about this is that I've drawn this as though the molecules in the solid are all the same, blue ovals. But in fact, what you might do is make mixtures or co-crystals of different molecules where the different molecules have different electron affinities and ionization potentials. So there's sort of a built-in driving force for charge transfer already in the identity of the molecules. So those are three good reasons why CT excitons might exist, and we need to talk about them. So before we go on, we want to have a discussion that is in the modern parlance called mind the gap. And this is where we carefully distinguish between the optical gap and the transport gap in a molecule or a molecular solid. The transport gap is also sometimes referred to as the fundamental gap or the charge gap, and this discussion has been going on for a long, long time in the organic electronics community, but we always have to revisit it. You'll see why. Very recent paper that discusses this gives us the title, Mind the Gap. by well-known theoretical materials and chemistry professor Jean-Luc Breda. So Breda wrote this very short paper with a funny title just to remind people of the difference between the types of gaps you find in organic molecules and solids. So in this diagram, you can see the point of the discussion where we've got the molecular exciton case shown as the S0 to S1 transition, and that transition defines the optical gap. It's the lowest energy optical excitation in the solid. And Breda points out that we need to be careful to distinguish that from the transport gap, which is the difference between the electron affinity or the ionization potential and the electron affinity of the solid, which essentially measures the excitation energy required to create separated free charges. And the difference between the two is exactly the exciton binding energy. And so this is just something that you always want to keep in your mind. In other words, the excitonic level S1 is different than either the ionization potential or the electron affinity of the material. And it can, if you're thinking quickly, it can be easy to sort of lose track of the meaning of all these terms. So again, the optical gap is this minimum energy for photon absorption, the S0 to S1 transition. The fundamental gap is the minimum energy to create free, fully separated charges with no Coulomb attraction between them. And so the fundamental gap by definition is ionization potential minus electron affinity. And then the optical gap is the fundamental gap reduced by the exciton binding energy. And so if you know the optical gap and the fundamental gap, you automatically know the exciton binding energy. That's an important tool to keep in your mind. I think it's a big if to know the fundamental gap for many interesting organic optoelectronic materials. It's actually not as easy as it seems to just measure IP and EA, even though conceptually they're very simple quantities. I just want to point out the first time I really started to understand this difference was with a paper that was published back in 2000, so 14 years before the Mind the Gap paper by Breda's close colleague Antoine Kahn and his student Ian Hill. They are photoelectron spectroscopy experts, which is one of the tools you can use to actually access the ionization potential and electron affinity of molecular solids. And they also point out that in the solid state, you have solid state polarization effects that change ionization and electron affinities compared to what they would be in the gas phase. And so there's a lot of complicated physics that can go into actually understanding band diagrams in molecular solids. Right? You've got many, many different contributions to excited states that are none of them very easy to access. But one thing to point out here is that, you know, in the in this paper, there's sort of a clear description of this quasi-hydrogenic Coulomb interaction between separated charges, and that can apply to whether they are separated within a molecule or between two molecules or even farther. And so there's definitely this idea that there's always this Coulomb attraction you need to think about overcoming as you separate the charges. So let's go back now to the question of CT excitons, and let's think about one of the most obvious ways to create a CT exciton. So you can invent a material where you would expect CT excitons by co-crystallizing an electron donor and an electron acceptor. So here we show the electron donor in blue, the electron acceptor in peach. And let's assume that we make an S1 exciton on the donor. So that's shown on the left here. Electron and hole pair on a single molecule. And then the idea is there's an energetic driving force for the electron to go from the donor to the acceptor. So there's, in other words, a downhill energetic funneling of the electron to go here so that the electron sits in the affinity level of the acceptor while the hole stays behind in the ionization level of the donor. And so this is just a simple way to see the driving force for charge separation in a purposefully designed donor-acceptor co-crystal, like an alloy. And this band alignment that you see here between the ionized donor and the ionized acceptor is called a type 2 band alignment in the jargon of semiconductor physics. And that's exactly the type of band alignment that you need to favor charge separation in any solar cell, and in particular in organic solar cells. This type of band alignment is really important to drive charge separation. And we'll see another example of that in a minute. So how do we know if we've got a charge transfer state, say, in a donor-acceptor co-crystal? There are a whole bunch of examples of donor-acceptor co-crystals in the literature. One relatively recent example that I found is this one, where you have this sort of small organic molecule where the donor is just a bunch of, it's basically just a hydrocarbon with some phenyl rings. And then you make an acceptor out of it by adding some very electronegative elements to the periphery. So you replace the hydrogens on the N groups with fluorine, and then you add these, I guess they're called azides. Maybe I'm wrong, I'm not sure. Cyano? I don't know. Anyway, nitrogen triple bonded to carbon. Just, again, sort of conceptually, you're just enhancing the electronegativity. So that makes the molecule a much stronger electron acceptor than the parent hydrocarbon you started with. And so if you co-crystallize this in a sort of alternating donor-acceptor pattern, you get a whole bunch of features in the optical absorption and emission spectra, which you can see here. And so then the question is, how do you know if any of these are CT excitons? And if so, how do you figure it out? And it's not easy. And this is really a research topic, figuring out to what extent you have CT character in your optically excited states is not an easy job. And in this case, probably the clearest evidence comes from theoretical calculations. I can't 100% remember what they did in terms of their theoretical methodology, but it doesn't really matter. The point I'm trying to make here is that by looking at the spectra, it's not so easy to be sure which, if any, of these have CT character. But then if you look at the excited state charge density differences, so differences between the excited state and the ground state, you see that the S1 state has substantial charge density on both the donor and the acceptor. So in other words, the state is located on both. Same is true for this T3 state, and then the other states are localized on either one or the other of the two molecules. And so by theoretical calculation, there's a clear evidence that S1 and T3 are CT in character. So S1 there refers to spin singlet, and T3 refers to triplet. But it's the third triplet, evidently. Okay, so that's one way that this can happen. And donor-acceptor co-crystals are pretty cool. They are right now not of enormous practical value for much of anything. Surprisingly, the thing that is of much more practical value is to make a super disordered donor-acceptor blend, where you just randomly intermix donor and acceptors in a kind of 3D jumble of spaghetti, right? And so this is a picture, a schematic picture of like the red is meant to be long polymer strands jumbled up like spaghetti bundles. The blue is meant to be small molecules where there's a little bit of crystallization, but there's also a lot of disorder. And you can mix in even a third molecule to sort of control how the blend is happening. And if you sandwich these between electrodes, they make pretty good solar cells sometimes. And so this is how you make what's called a bulk heterojunction organic solar cell. And in this case, if you choose the donor and acceptor properly, you can get type 2 band alignment between the donor polymer typically in this whole domain and the acceptor small molecule in this domain. So here the band alignment is, yes, it's between the molecules, but conceptually you're thinking of it more as between the domains of molecules. And so the type 2 band alignment, again, energetically drives some charge separation across the donor-acceptor interface. Say any place you see a red and blue interface should be a possible type 2 band alignment location where charges could separate. And then in principle, those separated charges can be moved away to light up a light bulb, do work as the photocurrent in a solar cell. And so the key insight here is that when you create an exciton in an organic molecule, initially it's a Frankel, really strongly bound molecular exciton. And you need this type 2 band alignment to be present somewhere to drive separation of that strongly bound exciton into free or quasi-free charges. And so without this really complex blend morphology where you have donor and acceptor domains touching each other almost everywhere, you wouldn't have any driving force to make an excited state separate into charges that can be used as a photocurrent. So it's a really different conceptual operation than a traditional silicon solar cell, where the exciton binding energy is so small that free charges are created essentially instantly by thermal dissociation of weakly bound Wannier excitons. And so this is a picture of the Jablonski diagram for an organic solar cell that shows sort of the complexity of the electronic states that you have to think about when you're thinking about how they work. And so we've got a situation where we've got an S0 to S1 transition that makes the S1 exciton in our, say, donor material in the blend. And then at the interface, there's a possibility to create CT-type excitons, and these are shown in green here. They're labeled by spin states 3 and 1, similar to how you would, label any singlet or triplet state. CT states can have, spin state associated with them. And then what you want to do is make the CT state further separate into so-called CS states, which are the charge-separated states that sort of qualify as free charges for making electrical current in an external circuit. And so figuring out how to design your molecules and your device so that all of these different states line up properly for efficient operation is a really important research topic. And it's not a solved problem. So like one of the examples is you create a CT exciton, say this CT1 in solid green here, and then what if this CT, you have a Coulomb binding energy between the electron and hole on different molecules? Somehow you have to overcome that. So how do you do it? And potentially that's an extremely inefficient process. And so there's a lot of thought in the literature that what really happens is you make the S1 exciton, and that dissociates into what's called a hot CT exciton, so a high energy one up here. So then there's a downward funneling from the hot CT exciton into one of the higher energy CS states, and then it's a little bit easier to make the truly charged separated state. And that's probably true for some choices of organic molecules in donor-acceptor photovoltaics, but not all of them. Yeah, so I guess I meant to point out here that this final state is the true charge separated state where you have IP of the donor and EA of the acceptor, and they're not Coulombically interacting at all. So that's this IP plus EA energy at the end. I guess, and another point that I want to make about the Jablonski diagram is each of these lines is really a whole set of orbital lines. So in a Jablonski diagram, remember, it's using one energy level to represent a full set of orbital energetics associated with a full excited state. But the situation is really complicated because there's a new class of acceptor molecules that have been invented in probably the last 10-ish years. It's probably slightly less than 10 years. And these are called the non-fullerene acceptors. So within this little picture here, which you can find in this review article, we've got non-fullerene acceptors like Y6, ITIC and IT4F here, BTRCL here, and then these. Actually, I'm not so sure about BTRCL. This may be also a polymer. But these 2 or 3 are non-fullerene acceptors. And one of the most interesting things about the non-fullerene acceptors is that it seems to be the case that there is no barrier coulomically to go from the CT state at the interface to the free charges, or the CS state, where the charges are completely separated from one another. And that's pretty surprising because, we do expect a CT state to have 2 opposite charges that are quite close to one another, about a lattice spacing. So you would really tend to call that still a Frankel type exciton. But in fact, it looks like there's no Coulomb barrier between CT and CS, which here is indicated as FC for free charge. And so that's a really cool aspect of these materials that was somewhat unexpected. They were actually designed to have lower energy optical absorption, to use more of incident sunlight to generate S1 excitons. But in fact, there seem to be a bunch of other really interesting properties about these types of molecules. And it's a really new topic. And so the question of why there's no Coulomb barrier is still essentially an open question. There's all kinds of interesting aspects of polarization effects, entropy effects, and really interesting and relevant to the modern literature is the possibility of hybridization between the S1 exciton and the CT exciton. That's in this case indicated as LE-CT hybridization, where LE stands for localized exciton. That's a jargon people use to talk about S1 a lot of times. So, but even in materials that have only one type of molecules, CT excitons are important. And so here I'm showing you 2 papers that my group collaborated on over the past couple years, where our theory collaborators at North Carolina Central University, led by Igor Bondarov and his colleague, I believe A stands for Adrian, but I'm not sure, Popescu. Anyway, these 2 guys did calculations to try to produce our optical absorption spectroscopy on an organic semiconductor called copper phthalocyanine. And they found that in order to produce the fine structure associated with these optical absorption spectra, they needed to include substantial sort of CT, LE hybridization effects, that you can't just assume that these are S1 excitons created on the molecule. You have to understand that there's a little bit of charge separation between adjacent molecules in these stacks. And it makes sense. There's an electronic coupling between them. There's no real reason why excited charges would stay perfectly localized on one molecule. And so CT excitons are really important, not just in donor-acceptor co-crystals or blends as in photovoltaics, but even in just understanding the optical properties of single component materials. So here's our map of different types of excitons that we've got so far. And this time we're basically in the space of Frankel excitons, where we have really small separations between charges. And we're thinking about the case where the separation between charges is just between adjacent molecules in a solid nearby. And what are the implications? And it's quite complicated. So let me point this out with some schematic points on this graph. So when we're looking out at the Wannier excitons, we know we can use a hydrogenic model, or we can just think about the binding energy decreasing as 1 over the separation between charges. No problem. And we think we can even extend that, again, based on this Barford paper about excitons and polymers, we think we can even extend that into the regime of Frankel excitons substantially. And maybe even, deep into it, where the spacing is starting to be like exactly a lattice spacing. But the situation is complicated because there are circumstances where it seems that the exciton binding energy for certain types of CT excitons can be almost nothing, almost negligible. And so we see that in the Frankel exciton regime, understanding exciton binding energy within a hydrogenic model, though it may be possible, is not necessarily going to fall on like a simple trend with other materials of comparable dielectric constant. Again, that's a completely open question. I'm sort of just being, a little bit provocative in this discussion by saying there's something really mysterious here. Maybe it's possible to do it all in a hydrogenic model, but there definitely a lot of work yet left to be done in figuring out what's going on in this small separation space. So that's all for CT excitons. The next species that we're going to do is even smaller, even more difficult to comprehend a hydrogenic model, where we look at DD excitons and other types of excitons that might even be located on single ions in a solid, not just single molecules, but single ions.